Hello everyone from Math 2000, Linear Algebra. It's Professor Winson here again with a video on your Zybooks section 9.5 titled Orthogonal Matrices. Okay, so let's just get right into it here. So some diagonal matrices can be diagonalized by a matrix that has an additional property called orthogonality. For an orthogonal matrix A transpose is A inverse. Alright, so this is what it's going to mean to be an orthogonal matrix. An orthogonal matrix is a matrix whose transpose is its inverse, making the inverse easy to find. In addition, every m by n matrix can be written as a product of an orthogonal matrix and an upper triangular matrix. Right, you're going to see this is called the QR factorization of a matrix, one of these objectives here. It's at the very end of the section. In physics, orthogonal matrices are used to transform information such as position and velocity between two different reference frames, such as the center of the Earth versus the center of an orbiting satellite. Again, we're not going to get into any of the physics problems, but just explaining that they're useful. Alright, so the first part of the section is on these things called orthogonal matrices. An orthogonal matrix A, right, that's n by n. Okay, notice these are square matrices are the only ones that can be orthogonal. It's a matrix whose inverse is equal to its transpose. Right, so as they mentioned up top, right, in the summary, A inverse is equal to A transpose. So an orthogonal matrix A satisfies, the following conditions. If you multiply the matrix by its transpose on either the left or the right, you'll get the inverse, the identity matrix. Right? That's what it means to be an inverse. Alright, let me show you a little animation here. I'll play this one. So remember the standard basis for R2, U1, 1, 0, and 0, 1. The standard basis for R2, that's an orthonormal basis. Right? These are orthogonal under the dot product, and they're both 1 unit long. Right? They're both unit vectors. Rotating the standard basis vectors by an angle of theta preserves orthogonality and normality. Right? So if you took the blue vectors and just rotated them, say counterclockwise by theta radians, you'd get these two red vectors, v1 and v2, that are still orthogonal under the dot product and are still 1 unit long. So rotation preserves, orthonormality. Right? If you have an orthonormal basis and just rotate those vectors, you'll have another orthonormal basis. The matrix R that defines, rotation by an angle of theta, this R here, this is an orthogonal matrix because its transpose would be its inverse. So what you're going to notice, so what this is telling us here is that an orthogonal matrix describes a transformation that preserves orthonormality. If you have a linear transformation whose standard matrix is orthogonal, right? Its transpose is its inverse. That transformation will take any orthonormal basis vectors and map them to another set of vectors that's also orthonormal. Right. It's a lot of big words there, but that's what an orthogonal matrix represents. when you're talking about, in relation to linear transformations. All right, so first example. It's pretty easy to check if a matrix is orthogonal. Just multiply it by its transpose. And if you multiply it by its transpose and you get the identity matrix, then your matrix is orthogonal. So I'm not going to write this one out here. And you just take the transpose, right? Remember, transpose is every row becomes a column, right? Just, basically you do a reflection across the main diagonal. And multiply the matrix by its transpose on the left or the right. And if you get the identity matrix, then that means the transpose is the inverse, and your matrix is orthogonal. Right. Okay, so I would leave these to you, and just follow the lead of this example here. Take this matrix, find its transpose, easy enough. Multiply them, and if you get the identity matrix back, then this matrix is orthogonal. Right, its transpose is its inverse. Same here. Take the transpose, multiply them. Now you might have to use certain identities, like remember trigonometric identities, like maybe hopefully you remember that cosine of an angle squared plus the sine squared was always equal to 1. That may come into play here. But again, I'll leave this one to you. It's not hard to check if a matrix is orthogonal. Alright, so now if you know you have an orthogonal matrix, it should satisfy certain properties as well. Okay. So an orthogonal transformation preserves both inner products. That is, multiplying an orthogonal matrix and a vector neither changes the length of a vector nor the angle between vectors. Right, as you saw up here, right, if this matrix R described, if this was the standard matrix for a transformation, you see how multiplying by U1 takes it to V1. It doesn't change the length at all. Multiplying U2 by this takes it to V2. It doesn't change its length. It's still length 1. And the angle between the blue vectors, when I apply the matrix transformation to it, that angle between the vectors is still 90 degrees. So that's what they're saying down here in this area. So suppose A is an n by n matrix with us, with the standard inner product on Rn, the dot product. Then the following statements are equivalent. Right? So that means if any one of these is true, they're all true, and if any one of these is false, they're all false. So if A is orthogonal, then the norm of A times a vector x will be equal to the norm of x, right? Multiplying a vector by an orthogonal matrix doesn't change its length or its norm. And the inner product of ax and ay would be just the same as the inner product of x and y. Again, multiplying vectors by orthogonal matrices doesn't change their inner product. Therefore, wouldn't change the angle between them. Some other properties of orthogonal matrices. If you know you have an orthogonal matrix, then the following statements will be true. A inverse will also be orthogonal. Because think about it. A inverse would just be the transpose. And the transpose of the transpose is A, and multiplying them gives me the identity matrix. So yeah, A inverse, which is the transpose here, will also be orthogonal. The determinant of an orthogonal matrix is going to be either 1 or -1. All right, now let me write that out. Let me show you why. All right, we don't need the calculator up. So hopefully you recall this, right? That the determinant of a product of two matrices was equal to the product of the determinants, right? And these are all square matrices that I'm talking about. So suppose A is orthogonal, right? If A is one of these orthogonal matrices, right, that just means that A transpose is the same as A inverse. Well, let's start with this. That means we know this, right? A transpose times A should be the identity matrix. Now, if I take the determinant of both sides, both matrices, right, that means the determinant of A transpose times A should be equal to the determinant of the identity matrix. But what is the determinant of the identity matrix? Well, it's always just 1, right? Because it's a diagonal matrix, right? Just 1's down the main diagonal. And using this product rule, right, the determinant, this is equal to the determinant of A transpose times the determinant of A, and this should be equal to 1. And another thing you might want to recall is that the determinant of any matrix is the same as the determinant of its transpose, right? This is going back to the chapter on determinants. Because you could just do for A, you could do cofactor expansion down, the first row. You'd get the same exact result as if you did the, cofactor expansion down the first column of A transpose. So they're the same. So this is the same as, the determinant of A times itself. So it's the determinant of A squared equals 1, meaning that the determinant of A has to be either 1 or -1, right? Those are the only numbers that when squared give me 1, only real numbers. Okay, so that was a quick little proof there of the second statement. So if you take, so another quick way to say a matrix is not orthogonal is if its determinant's not 1 or -1, right? If the determinant's not 1 or not -1, if it's neither, right, then you know right away that the matrix is not orthogonal. Now, that doesn't mean that if a matrice's determinant is 1, that it's orthogonal, right? There's lots of matrices whose determinant is 1 that is not orthogonal, right? You still have to do the check, is its transpose its inverse? Right? That's the definition of orthogonality for matrices. And then finally here, the rows and columns of A form an orthonormal basis for Rn. Very nice. So you see back up here, right? So here they told us, that, in the solution here that A is orthogonal. So these column vectors with the 7/25, 24/5, that vector, and the -24/5, 7/25, these column vectors should form an orthonormal basis for R2. And you can check that they're orthogonal, do the dot product, you get 0 between these two. And each vector has a norm of 1, or a length of 1 unit. Same thing would go for the row vectors with the 7/25, -24/25, that row, and the second row, 24/25 and 7/25 components. These two vectors also form an orthonormal set, that is a basis for R2. And that is going to happen in any orthogonal matrix. The rows will form an orthonormal basis for R2. The columns will form an orthonormal basis for R2. And then for a 3x3 matrix, it would be for R3, for a 4x4 matrix for R4, etc. So look at this example. So they're just saying, determine whether each statement is true or false. All right. So I'll write this one out, the first one. All right, so here's the matrix in that first part of the example. I'm going to look at the column vectors of this matrix. So I'll call this first column vector, v1, and I'll call this second column vector v2. Now, if A were orthogonal, right, I don't know that yet, but if A were orthogonal, then these column vectors should form an orthonormal set. So a question I could ask myself is this set with vectors v1 and v2, the columns, and orthonormal basis for R2? Okay. All right, so first I'll take, now again, they didn't specify any specific inner product, so I'm going to use the dot product as the inner product. So let's check to see if there, one, is the set orthogonal? First off, is every pair of vectors orthogonal? So I'm going to take the inner product of v1 with v2, which is the, just the dot product. So that'd be negative 2/9 plus positive 2/9. That's 0, so great. And that's the only pair of vectors in there. So the set is orthogonal, but that's only half the battle. Is the set orthonormal? So remember, that means that every, not only are the vectors orthogonal, pairwise orthogonal, but every vector is also a unit vector. So remember, let's take the norm of v1. Now hopefully you recall this is just the square root of the inner product of v1 with itself. All right, that's how we defined our standard norm. All right, so this is the square root. Now the inner product again is the dot product of v1 with itself. That'd be 1/9 plus 4/9. So I'm getting the square root of 5/9 here, which is not 1. That's not 1. So I don't even need to check vector 2. I don't need to check the second column. This set of column vectors is not orthonormal. And since that's the case, this matrix is definitely not an orthogonal matrix. Right, because in an orthogonal matrix, the column vectors will form an orthonormal set. Also the row vectors, will form an orthonormal set. Okay, so this is a false statement, as you see here, number 1, false. Okay. And then number 2, right, if A is an orthogonal matrix, then A transpose is also orthogonal. That basically comes from this statement here, right? A transpose is A inverse, and we already said that that would be an orthogonal matrix as well. Oop, I forgot I was showing this to someone else earlier, just one activity. Well, anyway, might as well go through these. How about these? If A is orthogonal, then 2A is also orthogonal. Well, remember, if A is orthogonal, that means the determinant will be 1 or negative 1. It has to be one of those two. If you multiply a matrix by a scalar, remember how that affects the determinant. 2A multiplies every single row by 2, which would multiply the determinant by 2 n times, whatever the number of rows is. So the determinant of 2A would not be 1 or negative 1, so it can't be orthogonal. Right, that's why this is a false statement. Number 2, right? If the determinant of a matrix is 0, then that matrix is orthogonal? No way, I just said. the determinant of an orthogonal matrix has to either be 1 or -1. Can't be 0. Also, again, I've said this already, just because the determinant is 1 or -1 doesn't mean it's orthogonal, right? It just means that it might be orthogonal. You still have to check, is the inverse the transpose? So be careful with that. All right. So the next part of this section, now that we've been introduced to these orthogonal matrices, is on diagonalization, but more specifically, orthogonal diagonalization. Now, we've seen diagonalization before, and it involved, finding the eigenvalues and eigenvectors of a matrix. And you can go back and hopefully brush up on diagonalizable matrices. Well, this is a similar concept, but a little deeper, a little further, called orthogonal diagonalization. All right. So a matrix A is orthogonally diagonalizable if an orthogonal matrix P exists such that P transpose, which would be the inverse of P if it's orthogonal, times A times P is equal to a diagonal matrix D. So remember when we were just talking about diagonalizable, you just had to find an invertible matrix such that P inverse times A times P was a diagonal matrix D. This is one step further. This is like, can you find an orthogonal matrix? Not just invertible, but a matrix whose inverse is its transpose. Can you find a matrix like that, such that the inverse times A, the transpose, times A times P is a diagonal matrix? So it's a little further, a little deeper. And they go into one more definition here because there's only one kind of matrix for which this can happen, for which you can find an orthogonal matrix P such that P transpose times A times P equals a diagonal matrix D. And those are symmetric matrices. Now, I think the word symmetric has come up before. It might have been a while. But just to refresh your memory, a symmetric matrix is a matrix that's equal to its transpose. So like this one here. If you looked at the transpose, it would be exactly the same matrix. So they call this symmetric, right? It is symmetric down the main about the main diagonal. So if you look at this spectral theorem here, which you can read the proof. Again, I'm not going to really read the proof to you, but I just want to read you the results. These are important. So suppose A is an n by n matrix with real entries. Number 1, A is orthogonally diagonalizable if and only if, so this goes in both directions, A is symmetric. So the only kind of matrix where you can do this, where you can find, the only kind of matrix A for which you can actually find an orthogonal matrix P such that this happens, the only kind of matrix which you can do that for is a symmetric matrix. So that makes it really easy to determine if a matrix is orthogonally diagonalizable or not. If the matrix isn't symmetric, then it's not going to be orthogonally diagonalizable. You won't be able to do this. And if it is symmetric, you will. It's that simple. Number 2, the eigenvalues of a symmetric matrix are going to be all, real numbers, no imaginaries. Number 3, the eigenvectors of a symmetric matrix A that correspond to distinct eigenvalues are orthogonal. This is another big one. So if you have two different eigenvalues, say lambda equals 1 and lambda equals 3, the eigenvectors corresponding to lambda equals 1 will be orthogonal to the eigenvectors corresponding to lambda equals 3. All right. That's another nice result. Right, and this didn't always happen for other matrices, right? But it will happen for symmetric matrices. And again, I'll let you read through the proof on your own. All right. So the procedure, how do we do this? Perform this orthogonal diagonalization. So the following steps are used to orthogonally diagonalize a symmetric matrix A. Again, it's got to be symmetric in order to even start this. So number one, find a basis for each eigenspace of A. That's probably going to take the longest. Right? You find all the eigenvalues of A, then find the eigenspaces corresponding to those eigenvalues, and then a basis for those eigenspaces. Right? That can take a while. Number two, apply the Gram-Schmidt procedure to the eigenbasis vectors to get an orthonormal basis for each eigenspace. So this is just for each eigenspace. You're going to try to get an orthonormal basis for each eigenspace using the Gram-Schmidt procedure, Gram-Schmidt process, which again can take a bit if there's a lot of vectors in your eigenbasis. Number three, form the matrix P that they're talking about up here. Right, this orthogonal matrix P. Form the matrix P using these orthonormal basis vectors from step 2 as columns. And that matrix P will orthogonally diagonalize matrix A, right? Meaning that P transpose times A times P will be equal to a diagonal matrix D. Furthermore, as with diagonalization before, the diagonal entries of this D matrix will be the eigenvalues of matrix A in the same order that you put those columns of P in, the corresponding columns of P. Alright, so I'm going to do this example here, and I'm really just going to do one of these. Alright, and then we'll move on. I'll let you watch my other videos. I do have other videos related to the topics in this section posted in Canvas. You can watch those. Alright. So I'll write this matrix out. We'll do it on paper. Okay. So notice that A is symmetric. Right? It is equal to its own transpose, meaning that A is what they call, again, orthogonally diagonalizable. Which means this. It means we can find an orthogonal matrix P such that P transpose times A times P will be D, where D is a diagonal matrix. Okay. So again, that's what I'm gathering just from the fact that A is symmetric. Now again, if A were not symmetric, you couldn't do this. Alright, so part one. Right. I'm going to break their step one into multiple steps. So first, let's find the eigenvalues. Right, so this is going back. Basically, find the spectrum of A. So remember, you're solving this characteristic equation, right? That when is the determinant of A minus lambda I equal to the number 0? this determinant of, and then I'm just subtracting lambda down the main diagonal, right? You got 3 minus lambda here, 3 minus lambda here, 3 minus lambda here, and then 1's everywhere else. When is this equal to 0? Alright, so I'll take this to the next page, and I'm going to do some cofactor expansion. Just go down the first row here. So this side we'd have 3 minus lambda times the determinant of, get rid of that row, that column. You got 3 minus lambda, 1, 1, 3 minus lambda there, that submatrix. Then, minus 1, because it's in an odd position, times the minor 1, 1, 1, 3 minus lambda. And then plus 1 times the minor 1, 3 minus lambda, 1, 1. Okay. Now these are nice, easy 2 by 2 determinants. So, when is this equal to 0, right? And, okay. So we have 3 minus lambda times. Now this should just be, 3 minus lambda squared minus 1. So, that'd be lambda squared minus 6 lambda. And then plus 9 minus 1 would be minus 8. Right. Then here it'd have 3 minus lambda minus 1. So that's just 2 minus lambda. Right. Plus, and then this is 1 minus the quantity 3 minus lambda. So this would be 2 plus lambda. Well, negative 2 plus lambda, so lambda minus 2. Right. 1, then minus 3 would be negative 2, and then minus negative plus lambda. Okay, and again, when is this equal to 0? Alright, so I'm noticing here this would be, 3 minus lambda. This factors to lambda. Oh, this would be plus 8, wouldn't it? Plus 8. I was like, what's happening here? Yeah, 9 minus 1. Alright, so lambda squared minus 6 lambda plus 8. Yeah, this factors to lambda minus 4 times lambda minus 2. And then I notice I'll have this is, if I pull a negative 1 out of here, this will be plus negative 2 plus lambda, or lambda minus 2, and I got 2 of them. So I have 2 lambda minus 2's. And then these now both have a factor of lambda minus 2. Pull that out. And what's left over is this product, get rid of this, get rid of that, and we got negative lambda squared, plus 4 lambda, plus 3 lambda would be plus 7 lambda. And then minus 12 plus 2 would be minus 10. Almost done. Pull a negative out. And that would give me lambda squared minus 7 lambda plus 10, which would factor to lambda minus 5 and lambda minus 2 again. Okay, so the eigenvalues, lambda of A, the spectrum, are 2 and 5. Alright. So now, again, probably should have paused that and moved ahead, but just wanted to remind you that this can take a while. Alright, so I found the eigenvalues 2 and 5. Now I would like to find, the bases for the eigenspaces corresponding to these eigenvalues. So number 2, eigenspaces. And again, you've done all this before. Right, so I'll start with for lambda equals 2. So remember, now we're solving this equation. Right? A minus 2i times some vectors equals the 0 vector. what vectors make this true, and those will be the vectors in your eigenspace. Alright, so what does A minus 2i look like? That's this matrix. So subtracting 2 down the main diagonal. And this is very easy to put into reduced row echelon form. I don't need a calculator for this. Just subtract the first, just take opposite, -1 times the first row plus the second and third row. You'll get 2 rows of zeros. And the first row is ones, and then again you got the zeros on the other side here. So I have 2 free variables. I've got 2 free variables, say x2 is s, and say x3 is t, where s and t are real numbers. And then from the first row, I'm seeing that x1 would have to be minus s minus t. And then putting all this together, we get our solutions here. The eigenspace of A corresponding to lambda equals 2 is therefore the span of the following vectors. Right now, one vector is with the coefficients of s, so -1, 1, and 0. And the other vector that is forming this basis here with the coefficients of t, -1, 0, 1. Right. So there's eigenspace of A corresponding to lambda equals 2. And then here's, that basis, just this set here, the set with these 2 vectors. This is a basis for this eigenspace, right? The set with the vectors -1, 1, 0 and -1, 0, 1. Now, unfortunately, it's not an orthogonal or orthonormal basis right now. We'll make it into an orthonormal basis later using that Gram-Schmidt procedure. Alright, so now for lambda equals 5. For lambda equals 5, doing the same thing. Right, here's matrix A. I'm going to solve, when is A minus 5i times some vectors equal to the 0 vector. So what does A minus 5i look like? Well, it's just subtracting 5 down the main diagonal. So -2 here, -2 there, -2 there. And 1's everywhere else. And I'll have the calculator do this one, put this into reduced row echelon form. I'll pop that right up on the screen for you here when I come back. Alright, so you see my reduced row echelon form pop up here. It's coming from a calculator. I put this 3x3 matrix into the calculator, did reduce row echelon form. Alright, so now take the calculator down. We got just the one free variable. I'll say x3, let's say that's t for some real number t, right? T is any real number. Then from the first row, we're seeing that x1 would have to be t as well. From the second row, x2 would also have to be t. So I got t times 1, t times 1, t times 1. So the eigenspace of A corresponding to 5 is the span of the set with the vector 1, 1, 1. Right. And there's a basis, just this set here, the set with 1, 1, 1. This is a basis for this eigenspace. Alright. Now I want to take these bases and do them separately. Right. So here is this set of 2 vectors is a basis for the eigenspace, corresponding to lambda equals 2. And this set with 1 vector down at the bottom here, this is a basis for the eigenspace corresponding to lambda equals 5. I'm going to take each of these bases and from them construct orthonormal bases to these eigenspaces. So I'll call this step 3. So we construct, and this is using that Gram-Schmidt procedure. construct, with Graham-Schmidt, that's an HM, construct orthonormal bases to the eigenspaces. So again, we'll go back to eigenspace corresponding to lambda equals 2. So the basis for this that I have right now is, the set with these two vectors, right? Negative 1, 1, 0 and negative 1, 0, 1. All right, so again, I'll call these, let's call these V1 and V2. Now, this is not an orthonormal set right now. If it were, I'd stop. I don't have to do anything. But this is not an orthonormal set. Okay, because look, you take the dot, again, the inner product here is the dot product. They didn't specify any other inner product. The dot product of these two vectors is 1, not 0. So these are not even orthogonal. And they're definitely not unit vectors. Okay, so now we have to use Graham-Schmidt to create an orthonormal. Well, first I'll construct an orthogonal basis, right? So first I construct an orthogonal set from these vectors. Say S equals U1 and U2. Okay, remember how this goes. U1 is just the first vector, V1. Okay, so U1 is going to be the vector negative 1, 1, 0. And then U2 is V2, but then you take away, right, you subtract the projection of V2 onto U1, onto all the previous U vectors, the vectors in this orthogonal set. So minus the projection of V2 onto the previous vector U1. Right? So this is V2 minus, and then remember the inner product of V2 with U1 divided by the inner product of U1 with U1 times U1. Right? So lots of stuff here. All right. So let's put these in. Now V2 is the vector, the second vector from my original basis, negative 1, 0, 1, minus, and then the inner product is the dot product. So what's the dot product of V2 with U1? Well, that's these two here. So that's just 1 divided by, and then the inner product of U1 with itself would be 1 plus 1 would be 2, and then times U1, negative 1, 1, 0. And we should get a vector that's orthogonal to U1, right? So let's see, we got negative 1, plus a half, so negative 2 halves plus 1 half, negative half for the first component. Then 0 minus a half, negative half for the second component. And 1 minus 0, 1 for the third component. Okay. And personally, I like doing this. Let's pull out the fractions. Say I take out negative 1 half here, and then that'd be times the vector 1, 1, negative 2. Okay, so there's U2. All right, so now I have an orthogonal set with U1 being negative 1, 1, 0, and U2 being negative 1 half, negative 1 half, 1. And then we'll just normalize the vectors. Normalize the vectors. All right, remember that means make them unit vectors. So just divide each vector by its norm. All right, so remember the norm is just a square root of the inner product with itself. The norm of U1 would be the square root of 2. Right? Because the inner product of u1 with itself is just 2. Then I take u1 divided by the norm of u1, and this will create a new vector. Let's call it w1. We get negative 1 over the square root of 2, 1 over the square root of 2, and 0. Right, there's a unit vector. Then the norm of u2, again, if you remember things about that, the reason why I pull out the scalars is for this reason. u2 is negative half times this vector, so that's just going to be half of the norm of this vector 1, 1, negative 2. Okay, and the norm of this vector would be the square root of 5. All right, because the dot product of it with itself is 1 plus 1 plus 4. I'm sorry, that's 6. I can't add. 1 plus 1 plus 4 is 6. So this is half the square root of 6. Right. So when I make a unit vector, when I take u2 and divide it by its norm, all right, that would just be, again, I'll call it w2. That would get rid of the halves here, because I would multiply by the reciprocal of this. This is the square root of 6 divided by 2. Dividing by is multiplying by 2 over the square root of 6. So that would make this negative outside, and then 1 over the square root of 6, 1 over the square root of 6, and negative 2 over the square root of 6 on the inside. And I can put the negative in. I get negative 1 over the square root of 6, negative 1 over the square root of 6, and positive 2 over the square root of 6. Right. And this is also a unit vector. Right. So now I have an orthonormal set, an orthonormal basis. This set I'll call S prime with W1 and W2. Right, this vector here with the square roots of 2 and this vector here with the square roots of 6. This is an orthonormal basis of that eigenspace. Corresponding to lambda equals 2. Alright, and what I'm going to do is, when we construct that matrix P later, this vector W1, this will be the first, I'll make this the first column of P. And this vector W2, with all the square roots of 6's in it, I'll make this the second column of that matrix P that will, orthogonally diagonalize A. Alright, so that was E2. Now I gotta do E5. Alright, now E5 won't be so bad because E5, its basis only has one vector. Right. So again, I just need to normalize. So this set, I'll call it S. What's the norm of this vector? It would be the square root of 3. The dot product with itself would be 3. The square root of 3. So I just divide every component by the square root of 3. 1 over root 3, 1 over root 3, 1 over root 3, and there you go. Here is an orthonormal basis for that eigenspace corresponding to lambda equals 5. Right. Yeah, when there's only one vector in the basis, real simple, just find its norm and divide by it. Right? Normalize the vector, make it a unit vector. All right, and then I'm going to make this vector the third column of P. All right, third column of P. All right, so this brings me to the next step. Once you've found these, once you've constructed these orthonormal bases for the eigenspaces, then the next step, construct matrix P that will orthogonally diagonalize A. And like I said, I'm just going to make these orthonormal basis vectors my columns. So from the previous page, my first column of P is this negative 1 over root 2, 1 over root 2, 0. I'll make the second column this other orthonormal basis vector from the earlier page, negative 1 over square root of 6, negative 1 over the square root of 6, 2 over the square root of 6. And the third column from that other eigenspace, this 1 over square root of 3, 1 over square root of 3, and 1 over square root of 3. Right. This, and I'll do this on my calculator, I'll show you on the calculator. This is an orthogonal matrix that diagonalizes A. So I'm going to enter this matrix on my calculator right now. So let me pull up a calculator. Hopefully you remember how to enter matrices. Right. Go to the matrix menu. I'm not going to do all. Make you watch me do all of this. So let's see, matrix A. No, let's get out of here. All right, I'm going to make this matrix B. All right, B. So instead of P on my calculator, it's B. All right. So I'm going to make it a 3 by 3, and then put these entries in. Negative 1 divided by the square root of 2. And then I'll come back when it's all done. Okay, so I've entered all those entries. Now I'll show you that this is an orthogonal matrix. Right? After all this construction, let's see that this is an orthogonal matrix. All right, so I'm going to take my matrix B here. Right? It's B in the calculator. So I'm going to take B and multiply it by B transpose. And I should get the identity matrix. So it's B, and then I go back to the matrix and go over to math and put in the transpose number 2 there. And look at that, right? The 3 by 3 identity matrix. So this matrix P that I've constructed here is orthogonal. Its transpose is its inverse. And now let's check the last part. Is the following true? Right? So is the following true? Let's take P transpose times A times P and see if I get a diagonal matrix. Now this diagonal matrix I know already, because remember it's going to come in the diagonal entries of this diagonal matrix will be the eigenvalues in the same order that I put the corresponding eigenvectors, right? The first two columns, they were from that orthonormal basis for the eigenspace corresponding to lambda equals 2, so I should have 2 and 2. Then this third column was from the eigenbasis for lambda equals 5, so I should have 5 here and then 0 everywhere else. And let me show you that this is happening. So again, on my calculator, P is matrix B, and I'm going to make sure matrix A is what we started with. Now matrix A on my calculator is not quite there. I just got to change that to a 3, all the diagonal entries to 3s, and then we'll have matrix A. Right? So here's matrix A, and let me test this. All right, let me go back to the main screen, and I'll take P transpose, which will be B transpose in my calculator. So B transpose times A, which is in my calculator matrix A, so that's nice, times B, right, which is P. On my calculator it's B, and look, I'll get this diagonal matrix with 2, 2, and 5 down the main diagonal. Wonderful. All right, so again, that can take a while. Right, that was only a 3 by 3. If you had a 4 by 4, 5 by 5, it would be crazy. Right? Still doable if it's a symmetric matrix. Remember, you have to start with a symmetric matrix, right? The only matrices for which this can happen, for which you can find an orthogonal matrix that diagonalizes it, is a symmetric matrix. Okay. So now that I'm done with that example, like I said, that's the only example of that I'm doing. I'll leave the rest, I'll leave others to you. So you can mess with this one and fill in all the blanks, all the details. Now they're giving you a lot here, but there's a lot of just true or false statements. All right, now finally, the last part of this section on something called the QR factorization of a matrix. Now this is for any m by n matrix, right? So far up to this point, you know, we've only been talking about square matrices or symmetric matrices, right? But they were all square. Here, we're going to take any matrix, right? So QR factorization factors really any matrix A into A equals, you know, Q times R, where Q is an orthogonal matrix. So Q will be square, Q will be m by m, and then R will be an upper triangular matrix. Right. QR factorization is useful in solving the least squares problem and in calculating eigenvalues. Right. And we're not going to really get into that, but they are useful. So here's what happens, right? You take the Gram-Schmidt process can be used to factor any m by m matrix n into this. So again, you think of the column vectors into the product of a matrix Q, right, with these column vectors Q1 through Q, whose columns are orthonormal, and an upper triangular matrix R. And if A is a square matrix, right, and it is invertible, this QR factorization is unique. Right. So here, any invertible matrix A can be uniquely written as A equals Q times R, where Q is orthogonal, right? It means its transpose is its inverse. And R is an upper triangular matrix with positive diagonal entries. Remember, upper triangular just means all the values on the diagonal and up. Those are the only places where there's going to be non-zero entries. Anything below the main diagonal will be 0. All right. So again, I'll let you read through the proof. All right. Now first, I'll play this animation here for you, and then I'll do one example. Okay. So they're asking here, you know, find the QR factorization of this matrix A, right, 3 by 3 matrix here. Let's see. For an invertible matrix A, the unique orthogonal matrix Q can be obtained by normalizing basis vectors from the Gram-Schmidt process. Right. So what they've done is they've taken the column vectors of A. Right. Now these column vectors don't form an orthonormal set. They apply the Gram-Schmidt process and make orthonormal columns. So these columns of Q are gotten by performing the Gram-Schmidt process on the columns of A. And then if you want, A to be equal to QR, and just multiply. If you want to find that R, just take A and multiply on the left by Q transpose, right? Because that would get rid of Q here. And R will be Q transpose times A, and that's what they're showing you here. And you see it's upper triangular, and down the main diagonal are positive entries. So I will show you an example of this, maybe not that 4 by 4. All right, so let me show you with this like 3 by 3 here. You could, should I do the 4 by 4? Alright, I'll do the 4 by 4. Alright, again, this is the only example I'll do of this, because this, this Gram-Schmidt procedure can take a while, as you've seen in previous videos, where previous sections with the Gram-Schmidt procedure. All right, so this one here, and I'll call these vectors, say v1, the column vectors, say v1, v2, or they were using a's, but whatever, v3 and v4. Now, these 4 vectors on their own don't form an orthonormal set. When you're trying to write this QR factorization, right? Again, Q will be an orthogonal matrix, so its columns will be orthonormal. And the way to find those is just simply, take the columns of A and perform Gram-Schmidt. And again, the inner product is the dot product here. All right, so first I'll construct an orthogonal set of 4 vectors, say u1, u2, u3, and u4. All right. From these vectors v1 through v4, the columns of A. All right, so again, u1 is simply v1. So 1, 0, 0, 2. And u2 is v2 minus, the projection of v2 onto u1. And I'm going to, after this line, I'll probably just stop writing the formulas out. All right, so that's, v2, 0, negative 1, 2, 0, minus, now the dot product of v2 with u1 is 0 plus 0 plus 0 plus 0. Hey, okay, so that doesn't matter. So u2 is just v2. And that's because these two are orthogonal. Their dot product is 0. Great. That saves me a little time. All right, then u3 is v3. All right, so the third column minus the, I'll just write projections, right? Instead of the formula, the projection of v3 onto u1 minus the projection, you subtract the projection of v3 onto all the previous vectors you've constructed in this orthogonal set. So minus the projection of v3 onto u2. Right. So v3 is the third column, so negative 2, 0, 1, 0. Minus, now the projection onto u1, do the dot product of v3 with u1, so that'd be negative 2 plus nothing plus nothing plus nothing, so negative 2 in the numerator divided by the dot product of u1 with itself would be 5 times u1 minus the projection of v3 onto u2, which is this vector here. Their dot product is 0, 0, 2, and 0, so there's 2 in the numerator. Divided by the dot product of u2 with itself would also be 5 times u2. All right, putting all this together, see the first components, negative 2 plus 4/5, so that's negative 10/5, sorry, plus 2/5. Negative 10/5 plus 2/5 be negative 8/5 plus 0, so negative 8/5 for the first component. Then nothing, nothing, and then positive 2/5 for the second component. Then 1 plus nothing, and then minus 4/5. 1 minus 4/5 would be 1/5. And then nothing, positive 2/5 times that 4/5 and 0, so 4/5. And I'm noticing here all these have a nice fifth in common. So U3 is going to be a fifth times the vector -8, 2, 1, 4. All right, and then finally U4. Right. So U4 is going to be V4, the fourth column of my matrix, minus the projection of V4 onto all the previous vectors U1, U2, and U3. So onto U1 minus the projection of V4 onto U2 minus the projection of V4 onto U3. Alright, so this will be a lot. So I'm just going to come back when this is done. Okay, so I did some calculator stuff just to quicken this up. So U4 is this vector here with all these 85th denominators, which I pulled out 2 85ths. You have 2 85ths times the vector -2, -8, -4, and 1. Alright, so you need to stare at that, pause it, look at the calculations, make sure they work. So now I've got an orthogonal set: U1, 1, 0, 0, 2, U2, 0, -1, 2, 0. U3 is this this -8/5, 2/5, 1/5, 4/5, and U4 the -4 85ths, -16 85ths, -8 85ths, and 2 85ths. All right, and then I normalize these vectors to get an orthonormal set, make them all unit vectors. So remember, that's just take every vector and divide it by its norm, right? So U1 divided by the norm of U1. Well, the norm of U1, remember, this is the square root of the dot product with itself. So that'd be the square root of 5. So I have 1 divided by the square root of 5, 0, 0, and then 2 divided by the square root of 5. And this is going to be the first column of Q of that orthogonal matrix, right? This will be the first column of Q. And then for the second column of Q, U2 divided by the norm of U2. So again, the norm of U2 is the square root of the dot product with itself. That'd be the square root of 5 again. So we'd have 0, -1 over the square root of 5, 2 over the square root of 5, and 0. And this will be the second column of Q. I'll just put second column. All right, then U3 divided by its norm. All right, so the norm of U3, well, let's see, the dot product of this with itself, I already put up here, is 85 25ths. So the square root of this would be the square root of 85 over 5, but I multiply by the reciprocal of that. That gets rid of the 5, puts square roots of 85s under all these components here. So it'd be -8 over the square root of 85, 2 over the square root of 85, 1 over the square root of 85, and finally 4 over the square root of 85. Those are all the components of the third, that's a unit vector now. And I'll make this the third column of Q. And then finally the fourth column, U4 divided by the norm of U4. Well, let's see, the norm of U4, U4 is right here. So basically, I would just get rid of this 2 85ths and find the norm of this, which again is the square root of 85, right? So I just put up the square root of 85 under all those components there, those whole number components. That's why I like pulling scalars out. So when you normalize, that's going to go away. -2 over root 85, -8 over root 85, -4 over root 85, and 1 over root 85. And this will be the fourth column. Right? So the matrix Q is the matrix they gave us, right? Look at the see the first column, 1 over root 5, 0, 0, 2 over root 5, and this was the second, this was that u2 over the norm of u2. This is the correct u3 over norm of u3, and this is the correct u4 over the norm of u4. So this is true. Right. And they go through the process here, right? Again, long process. Now to find R, as I mentioned, and I'll leave this to you, but to find that R, you want to write A equals Q times R. Well, if Q is orthogonal, then I could just get R alone. I can multiply on the left side by Q transpose. Right? The inverse of Q would be Q transpose. And this is how you find R. So if I make a matrix Q with these columns, right, these 4 columns here, just take the transpose, multiply it by A, and that'll be an upper triangular matrix. It will be, I promise you. All right, so just to save some time here, I'm going to say I'll leave that detail to you. I'll leave you to find that on your own. All right, and then see if this is true or not. All right, then for your challenge activity, and you're given a matrix, you're asked to find orthogonal vectors v1, v2, and v3 to be used in constructing the orthogonal matrix Q. So go through the same, use these 3 column vectors here, go through the Graham-Schmidt process, find those unit vectors that would be the columns of Q. All right. Let's see what the next level looks like. Yeah, so this is again find Q. Now the nice thing is they gave you the orthogonal vectors. You just have to normalize them, right? Because these aren't unit vectors, right? And in an orthogonal matrix, all the vectors are unit vectors. All the columns are unit vectors. So I think in level 1, actually, you just have to find the orthogonal vectors that you would get before you normalized, right? So get those get the vectors from the Graham-Schmidt process that you get before you normalize. Level 3, now it's find R. Now here they told you Q. So remember this R, this upper triangular matrix, if they're telling you what Q is, you just take Q transpose times A. And that gives you the R in the QR factorization. And then finally, you're given a matrix and asked to find the Q and then find the R yourself. All right, but it's only a 2 by 2, so that should be nice. That should be nice and simple, or relatively simple anyway. All right, a lot of stuff there, a lot of stuff. Orthogonal diagonalization. What does it mean for a matrix to be orthogonal? You got the QR factorizations, and again, I have other videos, separate videos on each objective in Canvas, not just this one long video here. So if you want to take a look at those as well, please do. All right, and then you have your additional exercises. Some of these are assigned, some are not. I would still recommend looking at all of them just to check them out and get more exposure to the material, maybe get better at it, get more practice. You also have the solutions you can look at to check yourself. But please, try to work on the problems. Try to work them out first. Before you look at the solutions. You're not going to learn anything if you're just copying solutions down and not trying. And I hope this video is at least a reasonable starting guide for this section. You're going to have to fill in some of the details, but that's the way it should be normally. And if you have any questions, of course, send me a message and I'll get back to you as soon as possible. And thank you very much for watching.